Hi everyone. Is the audio clear? Let me know. So let's continue this asynchronous counter. Okay. So in the asynchronous counter, we have already seen binary down counter. Now we will study binary up counter, and the same idea we will apply. Remember, the idea will not change. The idea is not going to change. So what you want? You want binary up counter. So what we want to do? So right now, actually, there is no electricity here. So that is the reason I have turned off my camera. Okay. So as soon as the electricity will come back, I will turn it on. Okay. So let's focus on this uh, binary up counter. So this is the concept that we need to study. So let's start. So first of all, let's create 3-bit binary up counter. This is what we will create. So let's create 3-bit binary up counter. Remember, if I don't give you like what is binary down or binary up, then what should be there? Binary up or down. Then what should be, then what is by default? By default, it is binary up counter. Okay. So when I directly say binary counter, then it simply means, if I directly say binary counter, it simply means I'm talking about binary up counter. Okay. So this is your binary up counter. The definition you already know. What is the definition? The definition is this: binary up counter will go like this: 000, then 001, then 0010, and then 011, and then 11100, then 101. Okay, and then you have 110, 111, and then you have 1000. This is your, this sequence is called binary up counter. Remember, this sequence, this counting sequence is called, okay, this counting sequence, what we call it, this counting sequence is called binary up counter. This counting sequence is called binary counter. Okay, now let's see. So how will you do this binary up counter? So what is the idea? So first you just look at the idea. Just look at the idea. So this is your MSB Q2, Q1, Q0. Now let's create this. So initially you have 000, then you have 001, then you have 010, 011, 011, okay, 100, 101, and then 110, and then 111. Correct? Okay. Okay. So electricity have come back now. So this is this is your now. In this, you tell me. So this is what you want, correct? And after this 111, after this you want 000. Okay, this is what you want. So tell me quickly. Tell me what is the idea. This is your LSB. This is your MSB. This is your LSB. This is your MSB. Can you notice in every clock cycle? In every clock cycle. In every clock cycle, who is changing? In every clock cycle, this LSB is changing. So I can say this LSB is changing in every clock cycle. So I can write this in the list of ideas. So the first idea, what is that? That LSB changes in every clock cycle. LSB is changing in every clock cycle. In every clock cycle. In every clock cycle, who is changing? LSB is changing. Okay, so this LSB changing in every clock cycle. So what you will do? So for this, what action you will take? You will, okay, clock. So just directly give the clock to LSB. Connect this clock. This clock you directly give to LSB flip flop. Okay, to give you directly you give this to LSB flip flop. Okay, very good. Now the next idea. What is the second idea? You tell me. When this Q1 will change. See, this will change in every clock cycle. This is changing in every clock cycle. Okay, it is changing in every clock cycle. Now tell me when this Q1 is changing. You can notice this Q1 is changing when we are, this Q0 is going from 1 to 0. This Q0, when it is going from 1 to 0, this Q1 is changing. Can I say from 1 to 0? When this, you can very easily see. When this is going from 1 to 0, then this Q1 is changing. When this is going from 1 to 0, when this is going from 1 to 0, this Q1 is changing. Okay, this Q1 is changing when we are going from 1 to 0. From 1 to when we are going to 0, then you can notice this Q1 is changing. So this Q1 will change when we are going. Okay, so I can say that when this Q1 changes, this Q1 changes. Okay, when this Q0 is going from 1 to 0, when this Q0 is going from 1 to 0. So now you tell me, Okay, remember Q1 must change when your Q0 is going from 1 to 0. Now you tell me, if we use, okay, if we use here, you tell me, if we use positive edge triggered flip-flop, if flip-flops are positive edge triggered, if flip-flops are positive edge triggered, if all the flip-flops are positive edge triggered, means they are positive edge triggered, then what you will do? If all the flip-flops are positive edge triggered, and if all the flip-flops are negative edge triggered, if all the flip-flops are negative edge triggered, remember what we want. Remember what we want. So if the flip-flops are negative edge triggered, then what it means? Then it means they will trigger when your clock signal, when your clock signal is going from 1 to 0. So in this situation, I can directly connect this Q0. Can I directly connect this Q0 to clock of Q1? Can I directly connect? Yes or no? Tell me. Can I directly connect this? Okay, so let me connect to the internet. Okay, so okay, so now tell me. Hmm. So can I say, if my flip-flops are negative edge triggered, then what I will do? Tell me. If my flip-flops are already negative edge triggered, means they are already triggered by 1 to 0 transition. If my flip-flops are already triggered by 1 to 0 transition, and this is what we want. Can you tell me yes or no? If my flip-flop is already negative edge triggered, it means my flip-flops are already triggered by 1 to 0 transition. By this transition, they are triggered, and this is what we want. Okay, we want that this Q1 should change when this Q0, when this Q1 should change when this Q0 is going from 1 to 0. And so what you can do, you can connect this Q2 to clock of Q1. And if flip-flops are positive edge triggered, then what I will do? If flip-flops are positive edge triggered, then I can connect this Q0 bar. Then I can connect this Q0 bar to clock of Q1. To clock of Q1, I can connect this Q0 bar. Okay, very simple. Now this concept is extremely simple. Yes or no? Now you tell me. Okay, now you tell me here. So when this Q2 will change, when this Q2 is going to change, this Q2, when this Q2 is changing, this Q2 is changing when we are going from this Q1 is going from 1 to 0. When this Q1 is going from 1 to 0, you can notice Q2 is changing. So this Q2 is changing when we are going from 1 to 0. So I can say, here I can say this Q2 changes. What you can say? You can say this Q2 changes when Q1 is going from 1 to 0. So the same idea you will apply. You will apply the same idea. So I can say this Q2 will change. This Q2 will change when. So here I can say this Q2 will change when Q1 is going from 1 to 0. Correct? Okay. So if flip-flops are positive edge triggered, then what I will do? I will connect this Q1 bar to clock of Q2. And if flip-flops are negative edge triggered, then I will connect this Q1 directly to clock of Q2. Very simple. Okay, now this topic is very simple. I hope you are finding this extremely simple now. Okay, so like this you can do the connections. So let me do one connection. Whatever connection you tell me. Negative edge triggered. Let's take negative edge triggered. Okay, so let me take negative edge triggered flip-flops. So I am creating 3-bit down count. Up counter. I am creating 3-bit binary counter, which is up counter. Okay, I am creating this. So let me take these flip-flops, which are negative edge triggered. So what I am doing, I am taking the negative edge triggered flip-flop. T flip-flops I am taking. All these are T flip-flops. So I want 3 bits. So I am taking, because I want 3-bit counter. So I am taking 3 flip-flops. Okay, and these are connected to 1. All of them are connected to 1. Now, what you will do? Let me assume these are negative edge triggered. Let me assume these are negative edge triggered flip-flop. So if these are negative edge triggered flip-flop, so what will happen? Tell me what I need to do. What connection? This I will connect. Remember, this is your Q0. This is your Q0. This is your Q1. This is your Q2. So this is your LSB, this is your MSB. So LSB should change in every clock cycle. So I will connect this to clock. Okay. Now what I need to do, tell me. Remember, when this Q0 is going from 1 to 0, then this Q1 should toggle. Okay, and this Q1, this flip-flop is negative edge triggered. So I can directly connect this Q1 to here, this Q0 to here, and I can connect this to here. Okay, so that's it. Very simple. Okay, so this concept is very simple now, very easy concept now. Okay, so this we have seen. Now let's make a timing diagram quickly. So let me make a timing diagram quickly. So the same thing you will do. The timing diagram, let me make it quickly so you can make the timing diagram like this. Let me make the timing diagram. But actually now you understand the concept. I don't need to make timing diagrams, correct? Okay, I don't need to create timing diagrams because now you already understand the concept. What is going to happen? What is going to happen? You already understand, right? Okay, so let's see. So this is your clock. This is your clock, and this is your Q0. So if propagation delay, assume propagation delay is 0. Assume there is no propagation delay. Then what will happen? Assume no propagation delay. Assume there is no propagation delay. Okay, then in this situation, what will happen? Then you can notice we have negative edge triggered or not. Okay, we have negative edge triggered. Our flip-flops are, we have taken the flip-flops to be negative edge triggered. Our flip-flops are negative edge triggered. Okay, so on the negative edge, what will happen? Initially, let me assume this is 0. Initially, let me assume this is 0. Initially, let me assume this is 0. This is Q1, this is Q2. Okay, so initially I am assuming all are 0. So on the negative edge, it will change. It will change on every negative edge. On every negative edge, it is going to change. Okay, it is going to change on every negative edge. Now you can notice, remember, all are negative edge triggered. All of them, all the flip-flops are negative edge triggered. So when this Q1 will change, when this Q1 will change, when this Q1 is going to change, tell me, when this Q1 is going to change, this is going to change. Okay, when in this situation, on the negative edge of Q0, on the negative edge of Q0, on the negative edge of Q0, when Q0 is going from 1 to 0, then this will change. And you can notice that this will change. This Q2, when the Q2 will change, Q2 will change when Q1 is going from, you can notice like this. Okay, so like this will happen. Okay, correct. So you got this. Now, so what is the sequence you got? Tell me, what is the sequence that we got? If there is no propagation delay, then which sequence we got? Initially, all are 0, 0, 0. All of them are 0, 0, 0. So from this 0, 0, 0, where are we going? What is the next state? The next state you can notice that is 0, 0, 1. Remember, this is MSB. Remember, this is MSB. And remember, this is LSB. Okay, so the next state is 0, 0, 1. And this is what we want, correct? So what is the next state? The next state is 0, 1, 0. The next state is 0, 0, 1, 0. The next state is 0, 1, 0. Okay, so the next state will be 0, 1, 0. What will be the next state? The next state will be 0, 1, 1. The next state will be 0, 1, 1. And so on, and so on. The next state will be 1, 0, 0. The next state will be 1, 0, 1. The next state will be 1, 1, 0, and so on. So like this will happen. Okay, then you will get 1, 0, 0. And then you will get 1, 0, 1. Then you will get 1, 1, 0. And then you will get 1, 1, 1. And then you will get 0, 0, 0. So we got our binary counter. Yes or no? We got our binary counter. This is our binary up counter. This is a up counter. Okay. Now you tell me, if there is propagation delay, then in this situation, what will happen? If propagation delay, interesting things will happen when there is propagation delay. Okay. So if there is propagation delay, if we have propagation delay, of flip-flop, or if propagation delay of flip-flop is, let's assume T, and that is non-zero, that is not equal to 0, then in this situation, what will happen? Now, see, very simple. This is your Q0 and this is your clock. And this is your Q1, this is your Q2. So what will be the waveform for Q0? So you can notice this will change on every negative edge. On every negative edge, this will change. So initially, if I assume this is 0, if I assume all of them are 0, if I assume, this is my assumption. So on the negative edge, on this negative edge, it should change. It should change, but it will change after some time. 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 Okay, it will take some time, right? It will take some time. It will change after some time. It will take some time. It will change after some time. Again, it will take some time. It will change after some time, after some time. So this propagation delay will be there. Okay, now you tell me, quickly tell me, what is this delay? What is this delay? This delay is, what is this delay? This delay. This delay is T. This is the propagation delay, which is T. Okay, I am assuming the propagation delay is T. Now, okay, so now you tell me what will be the waveform for Q1. The Q1 will change with every negative edge of Q0. So the Q1 will change with every negative edge. At this point, Q1 should change. At this point, remember, at this point, it should change. It should change. It should change. Okay, at this point, it should change, but it will change after some time. Okay, it will change after some time. Again, propagation delay. At this point, it should change. It should change, but it will change after some time. On this, it should change. It should change, but it will change after the propagation delay. So like this will happen. Now again, you tell me. Again, you tell me what is this? Okay. Again, you tell me with the respect to this. Remember, with respect to clock, what is this delay? With respect to clock. With respect to clock, what is this delay? What is this delay with respect to clock? This delay. This delay is a 2t. Okay, this delay is 2t, correct? With respect to clock, you can check. You can check with respect to clock. This delay with respect to clock, this is 2t. Okay. Now, what is the next? Now the next is this Q3, this Q2. Okay, so this Q2 will change in this situation. So it will change. It will change. Okay, it will change when Q. So at this time, this Q2 should change, but it will change after the propagation delay. It will change after the propagation delay. Now you tell me again. Now you tell me again. This delay, if you look at this delay from clock point of view, how much delay you got? TTT. Yes or no? You got TTT. This propagation delay you got, that is TTT. If you look at this delay, what is this delay? This delay is 3t. Okay, TTT. You can notice this is T, this is T, this is T. Okay, so you got 3t. This is the propagation delay. So this is the idea. Now you tell me, if there are many, I can say, if you have many, I can say this, many flip-flops, if you have many flip-flops, then what will happen? If you have Q and where this N is large, if this N is large, then this delay will become NT, correct? This delay, if you notice, this delay will become NT. Okay, so this delay, actually, this is the next boundary. This is the next boundary, but this delay will become very huge. This delay, if you notice, this delay will become NT. This delay will become NT. Okay, so this delay actually will become very huge. I can say this delay will become very huge. This delay will become very huge. So finally, I can say this delay will be NT. Okay, so this delay will become NT. So tell me, for the normal operation, what should happen? For the normal operation of in the ripple counter, this is a ripple counter. Ripple counter means asynchronous counter. This is a ripple counter, n-bit ripple counter. So this is a ripple counter. Okay, n-bit ripple counter. If you have n flip-flop ripple counter or n-bit ripple counter, you can call it n-bit ripple counter. So if you have n-bit asynchronous counter, then tell me what should happen for the normal behavior, for a correct behavior, for proper functioning. For proper functioning, what should happen? For proper functioning, if you want proper functioning, then what should happen? For proper functioning, I can say that the clock time period, I can say clock time period. This clock time period, this must be greater than, or I can say this must be greater than equal to, I can say NT. This must be greater than equal to NT. Where this T is what? Where this T is what? This is the propagation delay of one flip-flop. This is the propagation delay of a flip-flop, of one flip-flop. Okay, in the terms of frequency, what you will say? In terms of frequency, clock frequency, in terms of frequency, what you will say? In terms of frequency, what you will say? Frequency is the opposite of this. So you will say 1 by NT, but this will also change. This will also become less than equal to. So frequency must be less than equal to 1 by NT. Correct? So for proper functioning, this should happen. Okay, now let's see one more thing. What is that? So let's see the one more thing, that is transient states. that is transient states. So you can notice here, initially you are in this state 0, 0, 0. From this state, where you should go? You should go to 0, 0, 1. Will there be any transient state? Will there be any transient state? No, because there is only one bit changing. Can you confirm from the transition diagram? Can you confirm from the transition diagram? In the transition diagram, are we getting any, tell me, in this transition diagram from 0, 0, 0, from 0, 0, 0, are we getting this, from 0, 0, 0, when you go to 0, 0, 1, are we getting any transient state? No, there is no transient state. So where you should go from here? Where you should go from here? You should go to 0, 1, 0. How many transient states will be there? So first, you can notice who will change. First, who will change? Tell me. First, this will change. So this will change. This will change first, LSB. And then this second will change. Okay. So there will be one transient state. And can you confirm from this transition diagram? From the transition diagram, can you verify? Can you verify? Look at this time. Look at this time. Look at this small duration. Look at this small duration. This is 0. This is 0. This is 0. Look at this small duration. 0, 0, 0. After that, everything is fine. 0, 1, 0. So after that, everything is fine. For a moment, we got 0, 0, 0. For a moment. After this, what you should get? What you should get? Tell me. You should get 0, 1, 1. Will there be any transient state? Will there be any transient state? No, there will be no transient state. Can you verify from the diagram? From the transition diagram, can you verify? So from 0, 1, 0, you are directly getting 0, 1, 1. 0, 1, 1 you are getting. There is no transient state. You can verify from the diagram. Okay, after this, what you should get? What you should get? Tell me. After this, you should get 1, 0, 0. But what will happen? There will be some transient states. First, the LSB will change. Remember, LSB will change first. First, LSB will change. Okay, and then what will happen? Then this middle one will change. Then this middle one will change. And then finally, the last one will change. So first the LSB will change. Then this middle one will change. And finally, the last one will change. Okay, is this clear? Can you verify from the diagram? From the transition diagram, can you verify? From 0, 1, 1, from 0, 1, 1, we are going to 1, 0, 0. But in between, we are getting two transient states. We are getting two transient states. One transient state is 0, 1, one transit state is 0, 1, 1. One transit is, sorry, we are getting two transient states. We are getting. So, okay. So, oh no. So this transient states we are getting. One transit state we are getting 0, 1, 0. Correct. This transient state we are getting here 0, 1, 0. Look at this. Look at this 0, 1, 0 we are getting. And another transient state we are getting 0, 0, 0. Another transient state we are getting 0, 0, 0. So two transient state we have gotten. Can you notice? Can you verify? Can you verify from the diagram? Two transient states we are getting. Okay, very simple. Now after this, where I should go? Where I should go? I should go to 1, 0, 1. Will there be any transient state? No, there is no transient state. Okay, after this, where should I go? I should go to 1, 1, 0. There will be one transient state. What that will be? First the LSB will change, and then the middle one will change. First the LSB will change, then the middle one will change. Okay. Now after this state, where I will go? I will go to 1, 1, 1. I will go to 1, 1, 1. There is no transient state. And now you will get two transient states. You will get two transient states. First the LSB will change. First this LSB is going to change. Remember, this LSB is going to change. And after that, this middle person will change. So this 1, 0, 0. And after that, you will get this. So two transient states. So if they ask you in the exam, if they ask you how many transient states are there between this and this, then can you find it? Do you need to draw the diagram? Do you need to create the transition diagram? No, you can directly count. You can directly find. Okay, if they ask you how many transient states are there between these two, then that will be 2. How many transient states between these two? 0. How many transient states between these two? 1. Maximum how many transient states can be there between consecutive states? Maximum how many transient states can be there between two consecutive states? Maximum 2 transient states can be there. Maximum 2 transient states can be there. Okay, so this is the idea. I hope this point is clear. Now, can you notice one more thing? Why this is called ripple counter? What is the reason we call this ripple, this asynchronous counter? Why it is called ripple counter? This is my question. Why asynchronous counter is called ripple counter? Why asynchronous counter? First of all, why asynchronous counter? Why we call it asynchronous counter? Why we call it asynchronous counter? Tell me. First, you tell me this point. What is the reason we call it asynchronous counter? Why call it asynchronous counter? Because clock is not applicable on all the flip-flop. Okay, because all the flip-flop are not operated by the same clock. The reason you already know. Okay, same clock not operate, same clock not operating all flip-flops. Same clock is not operating all flip-flops. Okay, so this is the reason we call it asynchronous. This is asynchronous because you can notice that the clock will only apply to the first flip-flop. To the first flip-flop, the clock will apply. Okay, to the first flip-flop. This is your flip-flop number 1. After this, the output of this flip-flop will work as the clock for the next flip-flop. The output of this flip-flop will work as the clock for the next flip-flop. The output of this flip-flop will work as the clock for the next flip-flop. So this is the reason we call it asynchronous counter. Now you tell me why asynchronous counter is called ripple counter. Why asynchronous counter is called ripple counter? Why asynchronous counter is called ripple counter? Because this ripple effect is happening. This ripple effect is happening. You can notice, for example, if you are going from 000 to, for example, if you are going from 111, if you are going from 111 to 000, what is happening? The ripple effect will happen. The ripple effect will happen. Ripple means one by one. First LSB will change. The ripple effect will happen. First LSB will change. Okay, the ripple effect will happen. Then this will change. Then this will change. So the ripple effect is happening. This is called ripple effect. Okay, means this is called ripple effect. We call it ripple effect. Okay, ripple effect, one by one. Is it clear to everyone? Tell me why asynchronous counter is called ripple counter. This is called ripple counter because if you are going from this state to this state, then first this is changing, then this is changing, and then this is changing. Okay, then this is changing. So you can notice ripple effect is happening. This is the reason asynchronous counter is called ripple counter. Okay, now let's see the next point. So we have seen everything. So this is your up counter. Okay, now this is your diagram, correct? Now in this diagram, if I make, tell me, if I have negative edge triggered, this is positive edge triggered. So what should I connect? When you have positive edge triggered flip-flops, so what should I connect? Tell me, if we have positive edge triggered, so this 3-bit counter, this 3-bit binary counter, in this 3-bit binary counter, if we have positive edge triggered flip-flop, then what will happen? Tell me. If my flip-flops are positive edge triggered, if my flip-flops are positive edge triggered, if all the flip-flops are positive edge triggered, then what will happen? All the flip-flops are positive edge triggered. This is T. This is connected to 1, connected to 1, connected to 1. Okay, and now you can notice this will be connected to clock. And so what will happen? So you will connect this Q0 bar. This is your Q0 bar. Remember, this is your LSB. And this is your Q2 bar. This is your Q1 bar. This is your Q1. This is your Q2. This is your MSB. So what you will do, you will connect this to this, because remember, this is positive edge triggered. Okay, so we have already seen this idea. This idea we have already seen. So you can connect this to this. So this, if you do like this, then you will get a binary up counter. Okay, you will get a binary up counter if you make connections like this. So can you notice the same connection is happening here? Yes or no? This is positive edge triggered. This is positive edge triggered. All are positive edge triggered. All are positive edge triggered. And you can notice this connection is happening. And you can notice this connection is happening. You can notice this connection is happening. Correct? Okay, very simple. Okay, so let's move on now. So like this, you can check. Okay, all these slides you can go through. You can go through these slides. These are very nice slides you can go through. So can you notice that here you can notice propagation delay is increasing. Here you have some propagation delay. Now the propagation delay has increased. Now the propagation delay has increased more. Okay, so the propagation delay is increasing. The propagation delay gets longer. that is getting longer and longer. Okay, so this is the idea. So this we have already seen. Okay, so very simple. All these concepts you can read. Okay, after. So tell me when this will happen from 111. Actually, this will not happen, right? Actually, this is wrong here. So because first LSB will change. See, always you can notice because we are connecting. So first LSB will change. So this is actually it is wrong here. So first LSB will change. So what will happen? First LSB will change. So it will happen 110. Actually, this is correct here. Here it is correct, but here it is wrong. So first LSB will change. Then the second bit will change. Then the second bit will change. And then you can notice this bit will change. And then finally 000. Okay. So all these things we have seen. Everything, all these ideas. Okay. So like this you can do. And this you can see for the binary up, for the binary down counter. For the binary down counter, can you notice? For the binary down counter, what you will do? Tell me. For the binary down counter, what you will do? What you will do for the binary down counter? For the binary down counter, if you have negative edge triggered flip-flop, then you will do this. And if you have positive edge triggered flip-flop, then you will connect like this. This we have already seen. Okay. We have already seen this. So that's it. Now, what is the next question? So this is your binary counter. We have seen the binary counter. So far, we have seen what we have seen. We have seen binary count. This binary counter we have seen. So we have seen the binary counter in this down counter and up counter. Both of them we have seen. But remember what this binary counter does. So up counter will do this from zero it will go till, if you have n flip flop, tell me, if you have n flip flop, it will go till 2 power n minus 1. It will go till 2 power n minus 1 and then it will go here. So this will do. And if you have down counter, then what it will do? From 2 power n minus 1 to 2 power n minus 2, and then it will go like this, then 1, then 0, and then finally this will happen. Okay. Now you might be thinking, sir, can we create, like, okay, this is the question, how to create a counter, how to create a ripple counter. Ripple counter means asynchronous counter. So how to create ripple counter for this type of sequence, like 0 to m, for this type of sequence, 0 to, for example, 0 to 6 or 5. Okay, 4, 5. And then after that, you come back to 0. So this type of, basically, what this we will call it? What modulo counting is happening here? Tell me, which modulo counting is happening here? Which modulo counting is happening? Modulo 6 counting. This is your modulo 6 counting. This is your modulo 6 counter, I can say. This is the modulo 6 counter. Because remember why this is modulo 6 counter? Because there are 6 distinct states. Because there are 6 distinct states in this. Okay, in this there are 6 distinct states. So this is the modulo 6 counter. Okay, so now similarly you might be thinking, sir, can we go till any number? Can we go till any number? Okay, any number like this. Can we go till any number and so on? Okay, m minus 1. Can I go till any number m minus 1? Now what is this? What is this counter? This counter is what? This is your, I can say, mod m counter. This is your mod m counter. So can we create this type of counter? This you might be thinking. And the idea is extremely simple. Let's see the idea. And the idea is actually very simple. What is the idea? Do you remember? Let me tell you the idea. Every flip-flop, do you remember every flip-flop has 2 asynchronous inputs? Do you remember every flip-flop has 2 asynchronous input? Every flip-flop, we have already seen, every flip-flop has 2 asynchronous inputs. Do you remember those asynchronous inputs? Every flip-flop has 2 asynchronous inputs. In every flip-flop, there are 2 asynchronous inputs. Do you remember those asynchronous inputs? We have already seen clear and reset. Those asynchronous inputs, those are clear and reset. So this is your flip-flop. Any flip-flop you can take. This flip-flop, for example, you can take JK flip-flop. Okay, and this is your clock. Let's assume this is your clock. And in this JK flip-flop, what we have? This is J, this is K, this is Q, this is Q bar. In this JK flip-flop, what we have? In any flip-flop, what we have? 2 asynchronous inputs are there. What are these 2 asynchronous inputs? These 2 asynchronous inputs are there. So tell me, what are those 2 asynchronous inputs? One is reset. One is reset and another is clear. These are the two inputs. So one is reset, and these are active low. Yes or no? Do you remember? These are active low. Active low means when they are 0, they will work. When they are 0, they will do their work. So you have two inputs. Okay, you have two inputs. One is reset, one is clear. And what these inputs do? So tell me why we call them asynchronous inputs. What is the reason we call them asynchronous inputs? So there are two asynchronous inputs. One is clear and another is a preset. Another is preset. Another is preset. Okay, so another is preset. Now, why? First of all, these are active low. First of all, these are active low. What this means? When they are 0, they will do their work. Okay, now you tell me why we call them this asynchronous. Why we call them asynchronous? What is the reason we call them asynchronous? This we have already seen. What is the reason we call them asynchronous? Asynchronous input. Why they are asynchronous input? Because they don't depend on clock. They do not depend on clock. Yes or no? They do not wait for clock. They do not wait for clock age. Yes or no? They do not wait for the clock age. Correct or not? They will not wait. They do not wait for the clock age. Means what it means? It means what clock age is there or not. It does not matter to them. So this will happen. If clear is 0, then it will do its work. Remember, these are active low. Active low means when they are 0, they will do their work. When 0, they will do their work. When 0, they do their work. They do their work. When they are 0, they will do their work. So you can notice if I make this clear equal to 0, then what it will happen? Then what this will do? Then in this situation, what will happen? So it will clear the flip flop. It will clear the flip flop. Means the state will become 0. Clear the flip flop means state. Okay, the output will become 0. Output becomes 0. Correct? Output becomes 0. Now you tell me, if I have this situation, if I have like preset is 0, if preset is 0, now preset will work. Now preset will work. So what it will do? It will preset. It will preset the flip flop. Means output will become 1. Okay, output will become 1. And when both are 0, 0, when both are 0, 0, then this is not allowed. I told you this is forbidden, uncertain behavior. In this situation, you will get uncertain behavior. So never do this. Never make them 0, 0. In this situation, you will get uncertain behavior. Okay, so this is a forbidden. Okay, this is forbidden. Never do this. And if both are 1, 1, then what will happen? If both are 1, 1, then normal flip-flop behavior will happen. Normal flip-flop behavior happens. Normal flip-flop behavior happens. Okay. So can you notice one thing? Why these are called asynchronous? These are called asynchronous because they do not wait for the clock age. Means they will do their work immediately. They will do their work immediately. So as soon as whenever you make it 0, immediately it will do its work. Okay, the clock does not matter. It will immediately, I can say, will immediately clear. Yes or no? Will immediately clear the flip-flop. The flip-flop will be immediately cleared. Okay, the flip-flop will be immediately cleared, irrespective of the input. Similarly, this will immediately preset. It will not wait for the clock age. It will immediately do the work. Okay, so this is the idea. Now you tell me the idea. Okay, now you are going to tell me if I want to do this counting. This, for example, if I want to do this is my question. If I want to do this counting 0 to 1 to 2, then 3 to 4, 5. Okay, you tell me if I want to do this counter. First of all, how many flip-flop I need? I want to do this counting. This counting I want to do. How many flip-flops I need? Tell me. What is the number of flip-flop? What is the number of flip-flop I need? I need total how many flip-flop? So I need, because how many states are there? In this, you can notice total number of states. What is the total number of states? That is 6. So how many flip-flop I need? 2 flip-flop are enough or not? Can I say 2 flip-flop are enough? No. 2 flip-flop can give you 4 states. 2 flip-flop will give you only 4 states. Okay, so 2 flip-flop are going to give you 4 states. I want 6 states. So number of flip-flop, what is that? number of flip-flop needed. So that will be, I can say that will be, I can say log of 6 seal. So that will be 3. So 3 flip-flops are needed, correct? Okay. So like this. Now you think about the idea. How will you do? So you need 3 flip-flop. That is fine. So 3 flip-flop you need. That is fine. But how will you do now? Basically, from okay, as soon as sorry, after this 5, you should not go to 6. You should not go to 6. You should not go to 6. You should go to 0. So how will you do? Can you think? Think about clear and reset. Use clear and reset. Give me 1 minute. Okay. Hi everyone. Sorry. So you tell me now. Use the clear and reset. So what I'm going to do, see, very simple logic. Just understand the logic, and this is very easy. What I'm going to do, so this is what I'm going to do. Like, so when my circuit goes from 0, like okay, from 0 0 0, the circuit I will allow, the circuit should go to 0 0 1, then it should go to 0 1 0, then it should go to 0 0 1 1, then it should go to 1 0 0. It should also go to 1 0 1, right? It should also go to 1 0 1. Okay, correct. So tell me, this should happen for how many clock cycles? Like this should stay for how many clock cycles? This should stay. Like let's assume there is a display. There is a display. Let's assume there is a display. This is your display. Let's assume this is the display. On this display, these numbers are coming. So this number is coming. This number should come for how many cycles? For 1 cycle. For 1 cycle. In the next cycle, what should happen? In the next cycle, it should change. Correct or not? In the next cycle, it should change. In the next cycle. So in the after 1 cycle, it should change. So this was 0 0 0. After 1 cycle, this should change to 0 0 1. Okay, now you tell me, like this it will happen. Okay, after 1 0 0, after 1 0 0, after 1 cycle, this 1 0 1 should come. 1 0 1 should come. Now you tell me, should I immediately change it to 0? Should I immediately change it to 0? Like it's like, for example, 1 0 1 has come, and immediately I change it to 0. Should I do this? Hello, am I audible? So you what I am saying. See, for 1 clock cycle, this will stay. For 1 clock cycle, this will stay. For 1 clock cycle, this will stay, so that people can read. So people are standing here so that they can read. Now you can notice they are reading this. So you tell me, when after this 101, sorry, after this 100, this 101 will come. Now, should I immediately change? Like as soon as it comes, should I immediately change it? Like for example, 101 comes and you immediately change it. Should I do this? No, I should not do this, right? Okay, so I should not do this. I should not change this. This I should not do. Immediately. This I should not do. Okay, this is wrong. This is wrong. For one clock cycle, you should keep it. For one clock cycle, you should keep it. So what should I do? Tell me, what should I do then? Then what should I do? Then I will do this. So basically, when it will go to 110, when it will go to 110, immediately I will change it to 000. Immediately I will change it to 000. So for a moment, for a glitch, remember, for a glitch, for a moment, for a very small moment, this will come. This glitch will come. This glitch will come, but immediately it will become 000. Did you understand this? Please tell me. So a glitch will come. This glitch will come. This glitch will come, but immediately only this small, I can say very small, I can say very momentarily. I can say very small moment. For a small moment, this glitch will come, but then it will become 000. You won't even check it. You won't even feel it. Okay, this glitch will come. You won't even feel it. Like you won't even see it because immediately it will become to 000. But this glitch will come. Now you tell me. Now you tell me. So can I say what is this counting? Okay, basically this is counting. Yes or no? Basically this is the counting. Agree or not? This is the counting. Are you getting this point? Did you understand? There is a gate question on this. In 2015, there is a gate question on this topic. On this topic, there is a gate question. They are asking what is the counting sequence. They are asking what is this modulus. So tell me, if you have this type of situation, immediately if you change it to 000, then what counting we are doing? What counting we are doing? We are doing the mode. We are doing the mode 6 counting because there are 6 states. We are doing the mode 6 counting because don't say mode 7. This is mode 6 counting. This is mode 6 counting, not mode 7. Not mode 7. Not mode 7. So don't call it mode 7. This is mode 6 counting because this is coming for a moment. Okay. So just wait. Just wait. Okay, I am connecting to the internet. Actually, there is some electricity issue here. Some electricity is going, okay, coming, going, coming, going. So now I'm connecting to the internet again. Please tell me right now, tell me, did you understand what is happening here? So what we need to do, did you understand? So we need to remember if you are counting from 0 to 5, then from 0 to 5, everything should display for one cycle. For one cycle, you should display, correct? For one cycle, you must display. All these things you must display for one cycle. Okay. So now let's see. So this is what we are going to do. So you tell me what is the idea. So the same binary counter I will use, remember. So this is the idea, 0 to 1, 1 to 2, and so on to 5, and then 5 to 0. This is what we want. So now you will tell me what I need to do. First of all, what circuit I need to create? Binary up counter or binary down counter? What circuit I need to create? Binary up counter or binary down counter? Binary up counter. Okay, very good. So let me first create binary up counter. I am creating binary up counter. This is T, this is T, this is T. And I will connect this to 1. I will connect this to 1. I will connect this to 1. Okay, this clock. This is positive edge triggered and binary up counter. So what should I do? If these are positive edge triggered, then what connectivities I should make? This is LSB. This is Q0. This is Q1. This is Q2. This is MSB. This is Q0 bar. This is Q1 bar. And this is Q2 bar. So who I should connect? Should I connect this? Should I connect this or this? Tell me, which should I connect? Remember, this is binary up counter. I am creating binary up counter. So you tell me, should I connect this to this clock or should I connect this to this clock? Binary up counter. In the binary up counter, when your positive edge triggered, remember, when this will go from 1 to 0, then this would change. Yes or no? This is binary up counter. So when this will go from 1 to 0, then this would change. But this is positive edge triggered flip-flop. So I will do the connection like this. Yes or no? I will do the connection like this. Correct or not? Okay. This we have already seen. Don't worry about it. This concept we have already seen. Okay. So this is the idea. Now what I need to do? But this is counting what? This is not correct answer. This answer is definitely not correct. What is the reason? This answer is not correct because this is your binary up counter. Actually, this will do the counting from 0 to 7. This will do the counting from 0 to 7. Okay, so what I need to do, as soon as 6 will come, this is what I need to do. When 6 will come, means when they will become 6 means what? Tell me. Q2, basically, this is the idea. Idea is this. What is the idea? Idea is this. As soon as Q2, Q1, Q0, when they will become 6, as soon as they will become 6, as soon as they become 6, what should happen? What should happen? My counter should go to 0, 0, 0. As soon as this happens, counter should go to 0, 0, 0. My counter should definitely immediately my counter should go to 0, 0, 0. Immediately my counter, because I don't want this 1, 1, 0. This is undesired. Okay, this is undesired. I don't want this. I don't want this. This is undesired. So I should immediately should go to 0, 0, 0. What I need to do? Reset, right? Sorry, clear, right? Clear. I need to do clear. So this clear I will do. Okay, so what I need to do? I need to make a AND gate. So basically I need to make a NAND gate. This NAND gate I need to make. And this NAND gate, you can notice Q2 should be 1, Q1 should be 1, and Q0 should be what? Q0 should be 0. This connection I will connect to clear of all flip-flops. Is this clear to everyone? Let me know. Remember, Q2 should be 1, Q1 should be 1, Q0 should be 0. Q2 should be 1, Q1 should be 1, Q0 should be 0. This connection if I will connect this to clear of all flip-flops. So this is what I'm going to do. I'm going to make a this NAND gate I'm going to make. And I will connect this to clear of all. I will connect this to clear of all. I will connect this to clear of all. I will connect this to clear of all the flip-flops. But what will be the input of this? The input of this will be, I can say, this Q2. Input of this will be the Q2. Okay, Q2 should be 1. So when Q2 is 1, Q1 is 1, and this Q0 bar I can take. I can take this Q0 bar. Okay, I can take this Q0 bar. So this will happen. That's it. Now can you notice what will happen? Did you understand this? Please tell me, did you understand this? Now, if you do this, then what will happen? Let me tell you what will happen here. So if you do like this, then this will happen. Your Q2, Q1, Q0, they will go from 0, 0, 0, they will go to 0, 0, 1, no problem. One cycle. Remember, this is your, I can say, okay, this is after one cycle. Okay, if this is your cycle number, let me give cycle number. If this is cycle number 0, then this will happen in cycle number 1. And after one clock cycle, what will happen? Cycle number 2, it will become 1, 0, 0. It will become this. It will become this, and it will become this. And remember, it should remain cycle number 3, cycle number 4, cycle number 5. Cycle number 3, cycle number 4, cycle number 5. Now, remember, this should happen for one cycle. This should stay for, remember, should remain 5. This should remain 5 for one clock cycle. For one clock cycle, this should remain. For one clock cycle, this should remain. Now, as soon as in the next clock cycle, as soon as it will become 1, 1, 0, immediately you will change it to 0, 0, 0. Immediately you will change it to 0, 0, 0. Immediately you will change like this. Okay, in the same cycle, immediately you will change. So there will be a glitch. Like if you have, this is your Q0. Let's assume your Q0 is 0. Let's assume your Q0 is 0. Okay, so maybe let me assume this is the clock. Okay, clock is, we are taking positive edge triggered clock, right? We are taking this positive edge triggered clock. Now, if your Q0 was 0, if your Q0 was, Q0 was 1. Okay, Q0 was 1. Okay, here you can notice here Q0 was 1. Here Q1 was, so 101, 101. So this was 0, and Q2 was 1. So you can notice this is 0, this is 1, and this is a 1. Now, in this situation, When the next clock edge will come, what will happen? When the next clock edge will come, what will happen? Then they will become 110. Okay, they will remember this was 101. Now, when the next clock edge will come, they will become for a moment, they will become 1. For a moment, they will become 110. For a moment, they will become 110, right? For a moment, for a very small moment, the next clock edge will come. Like, for example, let's assume the next clock edge will come here. The next clock edge will come here. So you can notice for a very small moment, they will become 110 for a very small moment. And immediately what will happen? Immediately what will happen? Immediately the signal will go to, remember, immediately they are going to NAND gate. These signals are going to NAND gate. These signals are going to NAND gate. So immediately they will clear. All the flip-flop will become clear. Now you tell me one more thing. Please tell me one more thing. At this point, there is no clock edge. At this point, there is no clock edge. So can flip-flop clear? Can flip-flop clear? Why? What is the reason? Why flip-flop can clear? At this time, there is no clock edge. There is no clock edge. At this time, there is no clock edge. Then why flip-flop can clear? Because clear and preset are asynchronous inputs. Very good. Extreme. Okay, very good. Excellent. Because those are asynchronous input. So what will happen? Immediately they will become 0, 0, 0. Okay, immediately. Now immediately they will become 0, 0, 0. Immediately they will become 0, 0, 0. Immediately. So this is what will happen. I hope you got it. Please tell me. Did you understand this? So for a glitch, this I can call it a glitch. We can give this name. We can say that this is a glitch. We can say this is a glitch. This is a glitch. For a moment, we will get this 100, and immediately it will become 000 because clear will do its work. Okay, because clear is going to do its work. So that's it. Now you tell me one more thing. So did you understand this? Please tell me. This diagram, did you understand? That we are clearing the circuit. We are clearing the circuit. Okay. Now you tell me one more thing. Okay. So you know that I need to connect this. You know this that when this Q2, Q1, Q0, when this go to 110, then we basically this we connect to clear. This we connect to clear. This is what we do, correct? We connect this to clear. Okay, we connect this to clear input. Now, but you tell me, here can I say that this Q0 is don't care? Can I say this Q0 is don't care? Because it does not matter, right? These things does not matter. Are you getting my point? Can I say this Q0 is don't care? Can you say that Q0 is don't care? Can I say that as soon as they will become 1, it does not matter? It does not matter. As soon as they will become 1, I can connect to clear input. Yes or no? Because 111 never occurs. See, 111 never occurs. 111 never occurs. This will never occur. This will never occur. This will never occur. So this is the reason. 111 and 110. So combinedly they will make 11. Combinedly they will make 11. So I can say that this is a don't care. I can say 11 and this is actually don't care. So what connection I can make in this situation? What connection I can make? I can simply make this connection. This connection is enough. This Q1 connected here and this Q2 connected here. This connection is enough. Q2, Q1 is enough, right? This is enough. Because remember, anyway, this will never occur. This will never occur. And you can notice as soon as they will become 1, this is unwanted. Okay, both of them are unwanted. Both of them are unwanted. So I can say that as soon as this Q2, Q1 become 1, this I can say this situation is unwanted. Correct or not? I can say this situation is unwanted. Okay, this situation is unwanted. So this is a very simple topic. I hope you got it. Did you understand this topic? So what we are doing? So how many? Let's see one question. Let's see, and you tell me what just connection. You just tell me the connections. Now you tell me if I want this counter, like from 0 to 1 to 2 till 13, and then from 13 to 0. First of all, number of flip-flops needed. First to tell me how many flip-flops needed. How many flip-flops needed? I want to create a ripple counter. I want to create a ripple counter. So how many flip-flops are needed? So that will be log. You can take log. Okay, so that will be, I can say that will be 4. You need 4 flip-flop. Okay, now you tell me one more thing. So when I will, which combination I will connect to clear? When I will clear, so you can notice this 0 should have its own cycle. It should happen like this. See, 0 should have one cycle. This should be one cycle. This should be one cycle. This one should remain for one cycle, right? This also should remain for one cycle, correct? And finally, I can say this 40, this 12 should remain for one cycle. This should remain for one cycle. Okay. Similarly, this 13 should remain for one cycle. This also should remain for one cycle. Now what will happen? For a moment, for a very small moment, what you will get? For a very small moment, what you will get? As soon as it will become 14, as soon as it will become 14, for a very small moment, you can notice. Okay, let me make a very small moment. Let me make a very small moment. This is your 14. Okay, immediately what will happen? As soon as this happens, immediately it will become 0. Immediately it will become 0, and this should remain for one cycle. This diagram you understood, right? This is a nice diagram. Okay, I should have created this diagram earlier also. So let me actually create, so that by when you are reading this slide, at that time you will get to know. So basically this is the idea. Here you can notice that this is the idea, that you have these cells. This should happen. This should happen, that it should 0 for one cycle, 1 for one cycle, 2 for one cycle, 3 for one cycle, 4 for one cycle, 5 for one cycle. Okay, then for a moment this will become 6. For a moment this will become 6, and immediately what you will do? You will make it a 0. You will make it 0. Okay, so you can notice this is a one cycle. I can say this is one cycle. I can say this is one cycle. And similarly, you can notice this is one cycle. For one cycle, this should display. For one cycle, this should display. Okay, this diagram you can understand. You can understand using this diagram. Very small. Okay, for us, this is a glitch. This is just a glitch. So the same question I'm asking here in this, if I want this 13 from here to 13, then what I should make the connection? So there will be flip-flop. You know, there will be flip-flop. So which connection I should make? There will be 4 flip-flops. So there will be this flip-flop Q0. There will be this flip-flop Q1. There will be this flip-flop Q2. And there will be this flip-flop Q3. So which connection let me assume these are negative edge triggered. Let me assume these are negative edge triggered. So what connection I will make? First of all, you tell me what to this clock, what I will add. So first, you know that this is your T, this is T, this is T, this is T. All are connected to 1, 1, 1. All are connected to 1. Now you can notice this clock I will connect directly here. But you can notice now the Q0 will be directly connected. The QG1 will be connected. And here the Q2 will be connected, because I am doing the up counting. Okay, very simple. Now you tell me, but this circuit is for what? But this circuit is giving me what? This circuit is actually giving me 0 to 1 to 15, and then it is going to 0. This circuit is giving me binary counting. Okay, now I want 0 to 1 to 13 and then I should go to here. So for 14, in case of 14, what I will do? So when they become 14, this Q3, I can say this Q3, Q2, Q1, Q0. When they become 14 means 1110. In this situation, clear will be activated. In this situation, I can say clear all flip-flops. So when this happens, then clear all flip-flops. So can you notice two things you can do? What are the two things? Either you can connect it. So basically, I can say that two things you can do. Either you can connect, there is a NAND gate, you can create a NAND gate, and you can notice Q3 must be 1, Q2 must be 1, Q1 must be 1. And what this Q1, Q0 bar must, okay, this Q0 bar you will correct. Remember this Q0 bar you will correct here. This Q0 bar you will connect here. Okay. So like this. And this you will connect to clear off all flip-flops. This you will connect to clear off all flip-flops. So this is what you are going to do. So what I can do, I can create this. Okay. So this NAND gate I can create. I can create this NAND gate, and the NAND gate output will be connected to clear off all of them. Clear off all of them. This will be connected to clear off all of them. So these are the clear, I can say. I can say these are the clear. Okay. So the input of this, what is this? Q0 bar, right? Q0, I want Q0 bar and all these. So I can say this Q0 bar I want. This is your Q0 bar. This Q0 bar will be connected here. What else? This Q1 will be connected here. This Q2 will be connected here. And this Q3 will be connected. This Q3 will be connected here. Like this you will do. This is your circuit. Did you understand this circuit? Tell me. So as soon as you will become 14, as soon as it will become 14, it will become 0. As soon as it will become 14, okay, you will clear all the flip-flop and they will become 0. There are many questions. There are many questions in the GATE exam on this concept. On this concept, there are many questions. We will solve. But now this is very easy concept. What is the another idea? Can you notice this is don't care? Can you notice this 1, 1, 1, 1? These two both are undesired, both are unwanted. Can I say this? These are unwanted, both are unwanted. So I can say that Q3, Q2, Q1, 1, 1, 1. This is unwanted. I can say this I can clear all flip-flops. In this situation, I can clear all flip-flops. Okay. In this situation, I can clear all flip-flops. All flip-flops I can clear in this situation. Okay. So like this. So this is the idea. Okay. So what I can do, I can make these connections. Let me make. So this NAND gate I will connect to all the clears. Remember all the clears. I will connect it to all the clears. I will connect it to all the clears. Now these are the clears. So, but the input of this will be only, okay, you can make this input, this Q2 input, and this Q3 input, and this Q3 input. Like this. Okay. So very simple, right? This concept. Did you understand? Quite simple, I hope. Now you tell me, how will you connect the decade counter? Like if I want to do modulus 10, what connection you will make? Just tell me the connections. Just tell me the connections. I want mod 10 counter. Mod 10 counter is called decade counter. Remember? Decade counter. Decade counter. What is that? This name is given to which counter? Decade counter. The name itself is telling you. Decade counter. Which counting sequence is called decade counter? This counting sequence 0 to 1 to 2 and so on to 9 till 9, and then you come back. Means basically decimal digits. You are counting decimal digits. This is also called BCD counter. Another name is BCD counter. Okay, another name is BCD counter because you are just worrying about 0 to 9. Only 0 to 9 you are worrying about. So this is also called BCD counter. So now you tell me what connections you will make if you want mod 10 counter. What connections you will make? This is my question. What connections are you going to make? So very simple. This is your Q3, this is your Q2, this is your Q1, this is your Q0. So when they will become 11, right? When they will become 10, then you will, when they will become 10, then you will do the resetting. So in the last question, we have seen 0 to 13, and this is 0 to 9. This is actually 0 to 9. So when it will become 10, you will do the recounting. Yes or no? You don't want it to become 10 because decade counter will go from where to where? This will go from 0 to 9. This will go from 0 to 9. So you don't want to make it 10. You don't want to make it 10. So when it becomes 10, then what you will do? This you will connect to. Then in this situation, you will clear all flip-flops. In this situation, you will clear all the flip-flops. So what you will do? So I can say that basically 1 0 1 0. So you will connect like this. This should be 1. This should be 1. This should be 0, right? This should be 0. This Q2 should be 0. Q2 should be 0. And then this Q1 should be 1. And this Q0 should be 0. This should be 0. So this connection you will do. Yes or no? And you will connect this to all the I can say this you will connect to all the clear. These are the clear. You will connect it to all the clears. Very simple. I hope this point is clear. What is the another idea? What is the another idea? Tell me. What is the another idea? In this situation, you can clear. Or can I say, actually, can I say, in this situation, can I clear? Only these are enough? Can I say only these are enough? Can I say only these are enough? Only these are enough. Can I say only these are enough? Because all other things are unwanted. All other things are unwanted. All these things are unwanted. Can you notice all these things are unwanted? All these things are unwanted, right? All these things are unwanted. Yes or no? Tell me. Yes or no? So this 1 1, all other things are unwanted. Remember, all the remaining things are unwanted. You just fix it 1 1. You fix it 1 1. Then you can notice all these things are unwanted. These are unwanted. Sir, in 12, 1 1 0 0 Q1 is 0. I'm not getting. Zero one one zero. What is the doubt? Yuvraj, what is the doubt? I'm not getting your doubt. Fixing the Q3 and Q1 to 1 will not work. If I fix them to 1, 1 0 1 1, it will work. All these are unwanted, right? All of them are unwanted. See, I only care about this. I only care about this. I only care about this. But you can notice this is covered. This situation is covered. See, this situation is already covered. This situation is already covered. And these extra situations are also unwanted. These extra situations are also unwanted. Can you notice what I'm saying? These extra situations are also unwanted. So what we wanted to cover, we have already covered. Yuvraj, is this clear? See, this is what we wanted to cover. We only care about this. We only care about this. Okay, we only care about this. This is already covered. And the remaining that we are getting, these are also unwanted. The remaining that we are getting, these are also unwanted. Yes or no? These are also unwanted. And this is our prime target. This is our prime target. This is our prime target. Okay. So what I can do, I can simply Q3 and Q1, I can simply connect them. I can simply connect them Q3 and Q1. Very simple. This is what you can do. Tell me, these questions, are they clear now? Very simple. The next topic is cascading counters. This is extremely simple. If you have, let's assume you have a counter which does mod M. Let's assume this is a counter which is mod M counting, which is doing mod M counting, mod M counter. Another counter is mod N counter. How will you connect? How will you create mod Mn? Remember, mod M means this will divide frequency by what? Mod M means frequency divided by what? This will divide the frequency by what? This is mod M. So this will divide, if you apply clock here, then this will divide the frequency by M. Okay. Now, and if you give this some frequency you give here, if you give some frequency here, this will divide the frequency by N. Correct. So this will divide the frequency by, this is mod M. So this will divide the frequency by M. This is mod N. This will divide the frequency by N. If I want to create mn, then what I need to do? What I need to do? Just connect like this. Just connect like this. So just connect like this. This is your input clock. This is your input clock. Here you will get f by m, and then finally this input. This input is f by m, so it will divide by n. So finally you will get m by n. Like this, you can connect the ripple counters. Yes or no? You can create the ripple counters like this. Like this, you can do the ripple counters. Okay, very simply, you can create the ripple counters. The next, how will you create mode 1000? Modulo 1000, how will you create? Using decade counter. Using decade counter. How will you create mode 1000 using decade counter? 3 you will take. You will take 3. Okay, 3 decade counter you will take. Decade counter is also called BCD counter. I told you this decade counter is also called BCD counter. So what you can do? You can just connect like this. Just connect like this. This is your input. This is your input clock. And you can connect like this. So here the frequency will be what? If the frequency, you can notice here, if the frequency here is f, then frequency here will be the frequency of this will be f by 10, f by 10, and frequency of this will be f by 100, because input frequency is f by 10, so f by 100, and then finally this frequency will be f by 1000. Okay, so like this frequency division, have you seen in your real life? Have you seen this frequency division in the real life? Have you seen this frequency division in the real life? Have you seen the frequency division in the real life example? Can you tell me the real life example? In the real life, have you seen the frequency division? Our frequency is getting slow, right? Frequency is getting slow. You are dividing the frequency. In the real life, have you seen this frequency division example? Anyone? Is there any device in your home? In your home, is there any device in which one thing goes very fast, very frequently, one thing goes slowly, and another thing goes very slowly? Is there anything? Is any such thing in your house? There is a clock, right? A real life example is your clock. In this clock, the frequency, the second, in this clock, there is a second, I can say there is a second, what is that called? Second pointer something. So second hand, yes. So what does the frequency of this second hand? If the frequency is f, let's assume frequency is f, then what is the minute frequency? If the frequency is f, here if the frequency is f, then what is the minute hand frequency? Minute hand frequency will be what? That will be f divided by 60. And hour hand frequency will be what? What will be the frequency of hour hand? This will go very slow. This will go very slow. It will go like, okay, this will go 60 into 60. Correct? In 1 hour, you have 60 minutes. In 1 minute, you have 60 seconds. So this hour hand frequency is f. This is fast. This is very fast. This goes very fast. This goes slow. This goes slow. And this goes very slow. This goes very slow. So in the real life, you have seen this frequency division, right? Actually, what happens in the digital watch? Should I tell you? In the digital watch, what happens? In the digital watch, actually, what happens? Let me know. Let me tell you. This is what happens. This is your digital watch. Hour, minute, and second. Okay, so what happens in this digital watch? Actually, there are counters. There are counters. So you can notice there is a counter for second. Now, whatever is the frequency of second, whatever is the frequency of this second, what you will connect? You will connect to mode 60 counter. You will connect to mode 60 counter. You will connect this mode 60 counter. You will connect, and that will be connected to minute. That will be connected to minute. Are you getting my point? What I'm saying? Okay, because the frequency will divide by 60. So something like this. Anyway, we don't care about it, but you got the idea. You got the idea that frequency division happens in the real life in your clock. In the clock, this frequency division happens. You divide the frequency. Okay, let's see this last point. From anywhere to anywhere, how to count? Tell me, what is your idea? From anywhere to anywhere, I want to count. So what you will use? Like, I want to count from anywhere to anywhere. Use preset. Very good. Very good. Use preset. So if I want to count, for example, if I want to count from 3 to 7, 3, 4, 5, 6, I want to count 3 to 6. This is what I want to count. So what I will do? I will do like this. See, if I want to count from anywhere to anywhere, then what I will do? I will do something like this. Means, first of all, how many flip-flops are needed? First of all, how many flip-flops are needed? So here, okay, ripple counter. So you are doing the ripple, you are creating the ripple counter. You are creating the ripple counter. So here, first of all, you will use 3 counters, 3 flip-flops you will use. Okay, so let's use 3 flip-flops. Now in these 3 flip-flops, actually what will happen? Let me tell you. So actually this will happen. You are using 3 flip-flops. You are creating a ripple counter, asynchronous counter you are creating. But actually what will happen? That initially this Q2, Q1, Q0, they will start actually by 0, 0, 0. Okay, they will actually start by 0, 0, 0. Then they will go to 0, 1, 0, 0, 1. Then they will go to here. Then they will go to 0, 1, 1. Okay. Now after this, they will go to 1, 0, 0, 1, 0, 1, and 1, 1, 0. And we want from here, we want this. From here, we want this. Then this cycle will repeat. So let me actually tell you what will happen. This will happen. See, initially, when you turn on your computer, initially, when you start any digital circuit, does it perform immediately? Does it perform correctly immediately? No. It takes some time to settle. Yes or no? When you start your computer, it takes some time to settle. It will take some time to settle. Okay, this is the settling time. Let me tell you, this is the settling time. Like, okay, these things are just, remember the main loop is this. This is the main loop. I can say this is the main counting sequence, or I can say this is the modulo. Can you notice this is the repeating counting sequence? I can call it repeating counting sequence. This is the repeating counting sequence. So initially what happens? This is, I can say this is just a settle time. This is just a, okay, counter is settling. Remember, it is just counter is settling. In this situation, counter is settling. Counter is settling. Okay, so in this situation, counter is settling, and this is your main counting sequence. So what I will do here I will do like this. Very simple thing. So first I will create 3 counters. So let me connect. Let me take 3 counters. Okay, let me assume that you have up counter. So assume that you have a negative edge triggered. Assume they are negative edge triggered, and this I will connect to clock. And you can notice that this is your Q0, this is your Q1, this is your Q2. This Q0 I will connect here. This Q1 I will connect here. Okay, so like this. This is your LSB. This is your MSB. Okay, so this is the connection. Now this is the up counting. I am doing the up counting, right? Here I am doing the up counting. Correct. Okay, so this is the reason up counter I have created. But this is not correct. Definitely this is not correct. This is T, this is T, this is T. This is connected to 1, this is connected to 1, this is connected to 1. Okay, this is your up counter, right? Definitely this is your up counter. Actually, this is your binary up counter. So this is the binary up counter. Means it will do the counting like from 0 to 7, and then from 7 to 0. This will do the counting like this. But what we want? So what we want? Two things we want. That when your Q2, Q1, Q0, when this reaches 6, then what should happen? When this will reach 6, then what should happen? Immediately what it should change to? When you reach 6, then what should happen? It should change to 0, 1, 1. It should change to 0, 1, 1. It should change to 0, 1, 1. Okay, very good. It must change to 0, 1, 1. Okay, now. So when this reaches 6, then it should immediately it should change. Remember, immediately this should happen. So if I want to do this, then what I will do? Basically, I can say this I will connect to clear. Basically, I need to clear this. And I need to preset this. Yes or no? I need to clear this counter. This flip flop I need to clear, and these two flip flop I need to preset. Yes or no? Did you get it? So these two. Now what I will do? What connection I will make? So now you tell me what connection I will make. I will make this connection. This Q2, Q1, Q0. When it reaches 6. When it reaches 6. Okay. When it will reach 6 means when it will reach 6 means 110 means this Q2, Q1 and this Q0 bar. So when you reach 6, then what you do? This connection, this you send to clear off. Using this you clear, I can say using this you clear Q2, and using this you send to preset Q1, and this you send to preset of Q0. This is what we will do. Did you understand this? Please tell me. Please tell me, are you getting this point? What I'm saying, very easy point, that from 110 I directly want to go to 011. Immediately this should happen. So what I will do, I will connect. When you see 110, then you clear this. When you see 110, you clear this Q2 and you preset this Q0, Q1. So when you see this 100, remember, when you see this 110, then this will become 0. When you see this 110, like 110, when they become 110 means ultimately this is 1. Or I can connect, I can say like this is your Q0, and I can connect like this. So this is your 0. Now you can notice, so when they are 110, this will become 0. Okay, now you can notice, using this I will clear Q2, I will preset Q1, I will preset Q0. This is what I will do. So what diagram I will get? What diagram I will get? I will get this diagram, that let's assume this is the preset. Let's assume this is the preset. Let's assume this is the preset of all. Let's assume this is the preset. Let me call it preset. Okay, and let's assume this is the clear. And let's assume this is the clear. Let's assume this is the clear. Okay, so you have now what I will do, very simple. So I will make this NAND gate. I will make the input of the NAND gate. What that will be? The input of the NAND gate, that will be Q2. When you see 6 means Q2, Q1, 1 means Q2 should be 1. So this Q2 must be 1. I can say Q2 must be 1. And what next? This Q1 must be 1. And this Q bar I will take. I will take this Q bar, Q0 bar. Okay, so this connection. Now where I will supply this? The output I will supply where? The output I am going to supply where? This output I am going to supply. I will clear Q2. I will clear Q2. So I will supply this to clear of Q2. Okay, and where I will supply this? Where next I will supply? I will supply this to preset of this and preset of this. That's it. So did you understand all the things that we have seen? Okay, are you finding these things complicated? Tell me. All these things are logical. See, everything is logical. So if you understand the logic, all these things will become very easy. Did you understand? Please tell me. This concept, did you understand? Yuvraj is saying, sir, it should not change to 011. So Yuvraj is saying it should not change to 011 immediately after 110. It should wait for 1 clock cycle. Okay. Right. Okay. So what we have done a mistake. Okay. Actually, this is what we have done. Because it should, yeah, Yuvraj, that's correct. So let me change the question. Yuvraj, that's correct. What you have said, that is correct. Okay, that is correct. Okay, so let me change the question. What you have said, that is correct. Basically, 6 should not come. Sorry, basically 6 should not come. I can say 3, 4, 5, and then immediately you change. Okay, so actually 3, 4, 5. So 3, 4, 5. This is actually desired. I can say this is desired. This is desired. So what I will do? So basically the idea is this, that as soon as it becomes 6, immediately it should become 3. Yes, very good. Okay, so as soon as it will become 6, immediately it should become 3. Okay, so yeah, that's correct. And for this question, what you will do? Let's solve this question also. Like if I want to do, can you notice one more thing? Please understand one more thing. Initially, this counter will be in which state? Initially, this counter will be in which state? Initially, the counter will be in which state? Initially, this can be in any state. Please understand. See, state is determined by these. State is determined by these. State is determined by these. It's like this. For example, let me tell you that maybe this counter is in the state 2. Maybe this counter is in the state 010. At that time, you turn off your computer. Then when you restart your computer, where the counter will start? Basically, it can start anywhere, right? Agree or not? Your counter initially, it can start anywhere. We don't know where it will start. For example, if I ask you, when you start your computer, when you restart your computer, what will be the content of your memory? Can you say 0000? What will be content of your memory? Your memory. It can be anything, right? It can be anything. So similarly, initially, the content of this counter can be anything. But whatever is the content, it will settle. Yes or no? Whatever is the content, it will ultimately settle in this loop. It will ultimately settle in this loop. Whatever is the content, ultimately, your counter will settle in this loop. Yes or no? Your counter will settle in this loop. Now, let's see this. Let's create this one. 5, 6. Let's create this one. So here what should happen? When you go to 6, when you go to 7, this should happen. Q1. Okay, so when you go to 7, immediately you should change. This is unwanted. Remember, this is unwanted. So when you go to 7, then you should immediately go to 3. You should immediately go to 3. Okay. Now, so what I will do? Basically, I will clear this and I will preset these. I will clear this and I will preset these. So what I will do? I will connect this NAND gate. Okay, remember this Q2 should be 1. This should be 1 and this should be 1. All of them should be 1. In this situation, this I will get and this I will connect. Where I will connect? Using this, I will connect to clear of Q2 and preset of Q1 and preset of Q0. Preset of Q0. So that's it. Very simple. Okay, so this is your chapter. And now some questions. Let's say back to back some questions. Just quickly tell me this is the question of Gate Electronics 1987 ripple counter question. Can you tell me the answer? Now this is very easy topic for you. This topic is extremely easy for you. And this is a gate question. 1987 ripple counter question. Can you try? Can you try this? So a ripple counter is given. A ripple counter using negative edge trigger D flip-flop is shown. Okay. But tell me, does it matter? Actually, by this connection, does it matter? Are you afraid of D flip-flop? Because this connection is same as D flip-flop. See, remember, this D, if I make like this, this is same as what? If I make like this, negative edge triggered. So negative edge triggered. This is same as what? This is same as, these two things are same. These two things are same, right? These two things are same. Correct? You can notice these two things are same, right? Yes or no? So there is nothing to worry. There is nothing to worry. In this question also, you can notice this connection is made. Can you notice which connection is made? Which connection is made? So this connection is made. So you can, okay, you don't have to worry about it. So basically it simply means that T is 1. It simply means T is 1. Now you tell me the answer. Negative edge triggered you have, and this is a ripple counter. This is a ripple counter. Okay, and this is a negative edge triggered ripple counter. The flip-flops are cleared to 0 at the R input. So what is this R input? Tell me. What is this R input? This is the clear. This is the clear input. R input means clear, or I can say reset. This is the reset. Okay. The feedback logic is designed to obtain the counting sequence shown in the figure. This sequence you want. This sequence you want. Okay, you want this sequence. So now in this sequence, this is what you want. So tell me, what should I do here? Very easy question, right? What you want? You want from 0, 0, 0. Okay, so basically from 0 to 5 you want. From 0 to 5 you want. And then you want to go here. So what you will do? As soon as you will focus on 6. 6 is unwanted. 6 is unwanted. Arnab, 6 is unwanted. What is unwanted? Tell me what is unwanted. Unwanted is 6. This I can say this Q2, Q1, Q0. Okay. In the question, everything is given. Can you notice? Is it given in the question what is MSB? In the question, is it given what is MSB? What is MSB? Is it given? Yes, it is given. Where it is given? See this. MSB is given. In the question, everything is given. This is a very nice question. Very nice question. In this question, everything is given. That this is MSB, this is LSB, this is MSB. Everything is given in the question. Every information is given in the question. You tell me one more thing. You tell me one more thing. You tell me one more thing. What is that? Okay, you tell me one more thing here. If you do up counting, in the negative age triggered flip-flop, what should be the connection? If you do up counting, because ultimately we are doing the up counting, right? This is up counting we are doing, correct? We are doing the up counting. We are doing the up counting. So when you do up counting, and you have negative age triggered flip-flops, and your flip-flops are negative age triggered, then what connection you will make? If your flip-flops are negative age triggered, then this LSB you will connect to clock. And if you are doing up counting, remember you are doing up counting, then you will connect this Q0 to clock. Yes or no? This Q0 you will connect to clock, and this Q1 you will clock here. Agree or not? This is what you do. In the down counting, what you do? When you do the down counting and you have negative age triggered, then what you do? In the case of down counting, this Q0 bar you connect here, and this Q1 bar you connect here. Correct? So these things we have already seen. Now, so when you do up counting, this should happen. Is it happening in this question? Is it happening in this question? In this question, is it happening that Q0 is connected to clock? Yes. You can notice here. This Q0 is connected to clock. You can notice this Q0 is connected to clock. You can notice this, this is connected to clock. So everything is perfect. Everything is perfect as it should be. Everything is perfect as it should be. Yes or no? There is no problem. Okay, now let's focus on this. So unwanted is this Q2, Q1, Q0. So unwanted is this equal to, when it will become 6, that is unwanted. When it will become 6, it is unwanted. So what should be the answer? Now you tell me the answer. 1, 1, 0. So Q2 must be 1, Q1 must be 1, and Q0 must be 0. So what should be the correct logic? And you are connecting it to reset. So as cleared by at the reset. Which option is correct? Tell me which option is correct. Okay, so yes, this option is correct, right? This option is correct. We have already seen NAND. Okay, if you remember, so what you do, basically when this Q2, Q1, Q0, when they become 1, 1, 0, this is undesired. This is unwanted. This is unwanted, correct? This is unwanted. So what you will do? This is what you will do. Q2, Q1, Q0 bar. Okay. So ultimately what this? Ultimately this is F, and this is basically Q2, Q1, Q0 bar whole bar. And this you will connect to clear. Okay. Using this you will clear. So you will connect to clear. Tell me, is this question easy or not? Now this question is easy or not for you? Okay, so the answer is option A. This is your GATE exam question. And similar questions are also there in the GATE computer science exam, but let's solve the next question. GATE electronics, GATE ECE 1990 question. Let's solve this. Quickly tell me the answer. Yuvraj, actually, I think there is something problem in this actually. See, they will never do this because I think there is some mistake in the diagram. Okay, Yuvraj, there is some mistake in the diagram. There is some mistake in the diagram. Okay, let's see the next. No. Array, Arnab, this diagram, the mistake is on the internet website. This question I have taken from a website. Maybe on that website, this mistake is there. In the original paper, maybe the question was correct. Okay. In the original paper. Basically, this reset and preset, these are active low inputs. If they mention, they have to give you explicitly, they have to mention. Okay. If they want active high input, then they will mention it. They will give it. Okay. Now let's solve this question. What is the answer now? So for this question, we have already seen 4-bit modulo ripple counter, ripple counter, 4-bit modulo 16. Actually, what is this counter? 4-bit modulo 16 counter. This is actually your binary counter, right? This is binary counter because it is modulo 16. It is modulo 16. It is like from 0 to 15 and then coming here. Okay. Anyway, it does not matter. Uses JK flip flop. Does it matter? Does it matter? It is using JK flip flop. Does it matter? No, it does not matter. No problem. You already know JK flip flop, whether you use JK flip flop or you use, for example, if you use this, no problem. This is same as what? This is same as this. Okay, so both are same, no problem. Next, if the propagation delay of each flip flop is a 50 nanosecond, the maximum clock frequency, what will be the maximum clock frequency? You know the idea. In ripple counter, what happens? Tell me. In the ripple counter, what happens for proper functioning? For any ripple counter, if you have any ripple counter, then for proper functioning, ripple counter, proper functioning, when the proper functioning happens, this we have already seen. When the proper functioning will happen? Proper functioning will happen when your frequency, clock frequency, when clock frequency is less than equal to 1 divided by number of flip-flop multiplied by propagation delay. This is number of flip-flops. And this is propagation delay of flip-flop. The proof we have seen, correct? The proof of this statement we have already seen. So let's use it. Let's use it. So clock frequency should be, so I can say this f should be less than equal to 1 divided by nt. Okay, what is this 1 divided by nt? What is this value? This value is 1 divided by 4 multiplied by 50 nanoseconds. Okay, so nano, opposite of nano is, nano means 10 to the power minus 9. Nano is 10 to the power minus 9. So opposite of nano is giga. Opposite of nano is giga. And opposite of second is hertz. Yes or no? Opposite of second is hertz. 1 by second. 1 by second, that is hertz. That is hertz. Okay, so it will be divided by 200. Divided by 200. So the answer will be what? The answer will be, I can say, the answer will be 5 megahertz. The answer will be 5 megahertz. So the frequency should be less than equal to this. The frequency should be less than equal to 5 megahertz. So what is the maximum frequency? The frequency should be less than 5 megahertz. So the maximum frequency is 5. Okay, the question is asking maximum clock frequency. So that can be 5. So the answer will be option C. You can see answer is option C. Next question, GATE 1993 electronics ripple counter question, tell me the answer. All the concepts we have seen. Everything easy, Akash. Now everything is easy. I have full trust on you. Okay, I have full trust on you. Now you can solve every question of ripple counters. We have seen everything. Literally, we have seen everything. We have seen every idea, every logic, every counter, every circuit. Okay, what happens when you have positive edge triggered flip flop? What happens when you have negative edge triggered flip flop? What happens when you want to do down counting? When you want to do up counting? When you want to count from anywhere to anywhere? When you want to count from zero to anywhere? Okay, so everything we have seen, every single concept. And what will happen when propagation delay is there? In the ripple counter, if there is propagation delay, then there will be transient states. Or also, when there is propagation delay, then you can notice the final flip-flop, the last flip-flop, okay, that will have propagation delay of NT. Okay, so all the concepts you have seen, the ripple counter, when it will do the proper functioning, in which situation it will do the proper functioning, all these things we have seen. Now you tell me the answer for this question. So this is GATE 1993 ripple counter electronics, GATE electronics ECE 1993 question. So tell me the answer. A pulse train with frequency 1 megahertz is counted using modulo 1024 ripple counter. Okay, modulo 1024 ripple counter. So how many, tell me, how many flip-flops are there? How many flip-flops are there? Number of flip-flops, what is that? Modulo 1024 ripple counter. How many flip-flops are there? That is 10. 10 flip-flops are there. Built using JK flip-flop does not matter. For proper operation of the counter, remember, this is what we have seen. This is our favorite. For proper function of operation of counter, the maximum permissible propagation delay per flip-flop stage is what? So that is very simple. So frequency should be less than equal to 1 divided by NT. Okay, so you can notice that frequency is 1 megahertz. That should be less than equal to 1 divided by 10t. So t must be less than equal to 1 divided by 10 megahertz. Okay, 1 divided by hertz, what is that? 1 divided by hertz, that is second. That is second. So this will be, I can say it will be 0.1 nanoseconds. The answer will be 0.1 nanoseconds. Sorry, not nanosecond, no. This is 0.1 microsecond. But the answer is, but the question is asking nanosecond. But the question wants nanosecond. The question wants nanosecond. So what I can do? I can make it 1000 nanosecond divided by 10. I can write like this, correct? I can write like this. I can multiply 1000 above, 1000 below. So it will become 1000 nanosecond divided by 10. So that will be 100 nanoseconds. So the answer will be 100 nanoseconds. Is this clear? Let me know. 50 nanoseconds. The maximum permissible propagation delay per flip-flop stage, there is a pulse train of frequency 1 megahertz is counted using modulo 1024 ripple counter. You have modulo 1024. So that is 10. So you have 10 flip-flop. Okay. Built using JK flip-flop for proper operation. So did we do any mistake or is it correct? So you can notice frequency is less than equal to 1 by NT. So from here, N is equal to 10. So here I can say 10 is less than equal to 1 divided by 10 megahertz. I can multiply 1000 above, 1000 below. So that will make nano. 1000 divided by 10 nanosecond. So I think everything is correct. So 100 is correct. Yeah, 100 is correct. So this website, whatever is this website, this is wrong basically. So there is some website. I took these electronics questions from a website. Okay. And anyway, this is wrong. So the answer will be 100 nanoseconds. Now let's see the next. GATE question. GATE electronics 1999 ripple counter question. Again, tell me quickly, what is the answer? Now you are expert of ripple counter. You are expert of this, I can say, asynchronous counter. Now, whenever you see the word ripple counter, what you will think? What will come to your mind? 2 marks. Whenever you see this word ripple counter, automatically should come to your mind that, okay, I got 2 marks. Okay, I got 2 marks. So tell me the answer here. So here you can notice what is this doing. Actually, basically, you just have to focus here. Can you notice? Everything else is perfect. You can notice JK are connected to 1. Okay, JK are connected to 1. Everything else is perfect. There is no problem here. Everything else is perfect. You just have to focus on this AND gate. Okay, we are connecting this to preset. We are connecting this to preset. So actually what is happening here? This is a down counter. Yes or no? Actually, this is a down counter. Can you notice? You can check it out. You can check it out. This is a down counter. You can check it out. This is a down counter. Why this is a down counter? Tell me. Can you notice why this is a down counter? Because this Q is connected to positive edge triggered. These are positive edge triggered, and you are connecting. This is a down counter actually. Now let me ask you this question: if you want to create this type of 5 to 4 to 3 to 0, if you want to create this, then what you will do? If you want to create this, okay, means for example, sorry, if you want to create this, means from 7, if you want to go till let's assume till 2, from 7, let's assume you want to go 7, 6, 5, 4, 3 and 2. Okay, and then you want to go here. Then tell me what you will do. In this situation, what you will do? Means as soon as 1 is undesirable, yes or no? So in this situation, 1 is unwanted. In this situation, 1 is unwanted. Means this Q2, Q1, Q0, when they will become 1, then what you will do? Then what you will do? When they will become 1, this is unwanted. So what you will do? Tell me. When they will become 1, then you will immediately change it to 7. You will change it to 7. Okay, immediately. You will immediately change to 7. So for that, what you will do? You will connect to preset. Yes or no? Very good. You will connect to preset. So these things you will do the preset. So preset you will do. You will do the preset. So what you will do? You will do like this. Remember, preset is active low. Preset is also active low. Preset is also active low. We know this preset is also active low. This is also active low. So what you will do? So when you see this 0, 0, 1, means this Q2 bar, Q1 bar, and Q0. So this is how you will do. Then you will connect to preset of all the flip-flop. So now you tell me the answer here. So what is undesirable here? Undesirable. You are connecting to, and this is a down counter. You can notice this is a down counter. So this you are connecting. Okay, actually, so you are taking this Q2. Can you notice? You are taking this Q2 bar. This Q2 bar you are taking. And what else you are taking? This Q1 you are taking. And what else? This Q0 bar you are taking. Okay, this is unwanted. Actually, yes or no? This is unwanted, correct? Because we connect only unwanted. So this is unwanted. So what is unwanted? Tell me. So unwanted is 0, 1, 0. This is unwanted. 0, 1, 0 is unwanted. So I can say unwanted is 0, 1, 0. This is unwanted. So what is happening here? What this counter is doing? Basically, this counter is going from 1, 1, 1. This 0, 1, 0 is unwanted. 0, 1, 0 is unwanted. So this is going till 3. This is going till 3. Okay, this counter, this is going till 3. So that's it. And you can notice this 0, 1, 0 is unwanted. So what is this counter? From 7 to 3 you are going. You are going till 3. So how many states are there? 3, 4, 5, 6, 7. Total 5. So answer will be mode 5 count. Mode 5 down counter. Remember? Sorry. Mode 5 down counter. Okay. This is a mode 5 down counter. So the answer will be this. This is, so the answer will be D. We have already seen. Okay, that's it. So there are some more questions in the GATE exam. There are many questions from ripple counter. Now what I will do? Today I will give you all the GATE exam question. Okay, this is what I am going to do. I will provide you a homework. I will provide you in that homework all the GATE electronics, all the GATE computer science questions of of this ripple counter. Okay, so for the ripple counter, every gate computer science question, every gate electronics question, these will be in that homework. You can try. Okay, and we will discuss after some days. So actually, there we will need one more day for counter digital logic. So on Sunday we will study digital logic. Okay, so basically, asynchronous counter is over, ripple counter is over. Let me tell you that we have studied everything. Okay, I promise you, no new question can be created. We have seen everything in the ripple counter, in the asynchronous counter. Okay, all the questions that can be created, we have seen. Okay, so in the on the Sunday on Sunday we will have this digital logic class, and we will study the last topic, that is synchronous counter. Also one small topic, that is NAND NOR realization, that also we will study. But on the Sunday we will study synchronous counter. Okay, anyone has any doubt, let me know. Arnav is saying, sir, I joined late, but you explained me why frequency divided by. Oh, okay, Arnav, thank you. Any other doubt? Anyone has any doubt today? Please tell me. Very logically, we have studied the every concept, every single concept. Logically, we have studied. I hope you will never forget. I hope you will never forget these topics. These are very interesting topics. Synchronous counter, asynchronous counter, all these things are very easy. If you understand these things, you will never forget. Like I studied them in 2018, 2019, and still I remember these things. Okay, because these things are so logical. You can logically create them. You can logically think about them. Whenever you have some difficulty, if you have forgotten what to do, just use the logic that we have seen. You don't need to remember any circuit. Okay, you don't need to buy heart any formula. Just logic you understand, and then from the logic you can create every circuit that you want to create. Okay, thank you everyone. So on Sunday we will study digital logic, synchronous counters. Okay, and tomorrow we will study TOC. So theory of computation will continue tomorrow. Okay, thank you. Good night.